Hello, and welcome to the channel. Today we're talking about what a container is really, but this is part 2. We've already looked at all the pretty pictures, but now it's time to do the practical stuff. So let's go. Linux namespaces are what creates the isolation required to make a container happen. There are many different namespaces, and Runcy uses a bunch of them. Let's run a container and do some investigating. We're going to use the -d command here to daemonize our container or run it in the background, --rm to remove it once we're done, --name to give it a friendly name of Ubuntu, and then lastly we're going to pass out our command here. We're going to use bash with -c so we can pass it sleep infinity. This is a nice way of passing bash a long command, and this will stop our container from dying when we run it in the background. Now we'll use docker inspect because we're looking for a very specific piece of information about this container. We're looking for this process ID. Now you'll notice it's nested under this array here, under the state key, which is also under that, the PID key is nested. You'll see we'll use the JQ syntax that kind of matches where it is. We'll use open square bracket, close square bracket, dot state, dot PID. JQ is going to filter that JSON and just return the PID to us. We're going to note this PID down because we're going to use the lsns command and grep for the namespaces that match our process ID. Now you'll see there are a bunch of namespaces at play here. We have the mnt namespace. This controls mount points that will be used for the root file system in the container. UTS, this isolates things like the host name and the network information services domain name. IPC isolates inter-process communication. PID isolates the process ID number space so we can duplicate process IDs in the container and it won't affect the system. Net virtualizes the networking stack. And then lastly, we have cgroup, which will control the resources used by the container and limit them. So now with all these namespaces at play, we can investigate a bit deeper using the nsenter command. But let's first look at the nsenter command itself in a bit more detail first. You'll notice we're not talking about containers when we use nsenter. The keyword here is process. We are running commands of the namespaces of other processes. So let's investigate our mount namespace here. We'll use -t to target our process here, -m to mount the storage inside of the container, and -e to pull in the environment variables. We're interested in getting the path environment variable here, which I go over conveniently in the short linked in the right hand corner above. So we're going to list out our home directory. You'll see that it's Ubuntu compared to our local directory. That is very different. So just to prove that we are actually inside of this container and looking at its storage, I'm going to go ahead and use exec to create 2 files inside of this file system. We're going to use the touch command to create something inside of this home Ubuntu folder. And then after we've done that, we go ahead and just run that again, but create something else. And if we run the same command and list out the storage for home Ubuntu, you'll see that both of these files now exist. So now let's use our trusty nsenter command to look up the UTS namespace here. We're going to use -u here to mount the UTS namespace, and you'll see we get this randomly generated host name. And let's compare that with our container, and we'll see that they're exactly the same. So to investigate the IPC namespace, we can actually make some IPC resources and see if we can access them from the container. Let's start by making some in the normal system. Let's create the shared memory segment of 10 bytes. And then let's create a message queue. And just to confirm it's there, we'll run IPCS. And we'll see these keys here. Let's just show what sharing with the host looks like in comparison with having a private IPC namespace. In our normal container, if we mount the IPC namespace and mount namespaces as well as the environment, we can't see any of these keys at all. Now we can go ahead and run a new container that shares the host's IPC namespace to see the difference. So when we run this, we're going to use our handy docker inspect command to grab that PID. Now we remember how we did this from the last time. And let's do the same test. Now when we run this, we should see that we can actually see the keys from our system. So I'm just going to quickly go ahead and run the ipcs command here. And we're going to grep for anything that looks like hexadecimal, and you can see both these keys match the keys here for the IPC resources. So now if we jump into our container and we just mount all of the namespaces for simplicity using the -a flag here, and we use bash, let's check the processes. Now you'll notice that the first process initiated in the container has a process ID of 1. Without the PID namespace, this would not be possible. Let's compare some of these processes to our local system. So if I run ps1, you'll see that it's quite common that system D usually takes process ID 1. And if we also check any of the other processes that are running in the container here and compare them to our local system, you'll see we have processes that have a completely different name running, and they are not conflicting with the process running in the container. This is what the PID namespace does. Let's see what we have in the networking namespace. So we're going to just list our IP addresses here, and we can check and compare this with our networking information inside of Docker, and sure enough, the IP address matches that from the container. Now to investigate the cgroups namespace, we're going to have to put some limits on our container. So let's start by giving it a memory limit of 50 MB and CPUs 0.5. We'll go ahead and run this guy. And then we'll use our handy docker inspect technique with JQ to get our PID. So we're going to see where the cgroups assigned to this container live. We're going to do that by using the ps command and using the -o flag to give us the cgroup of this process. Generally, we can find cgroups info in the /sys/fs/cgroup directory, so we're going to append the path that we see above here with that path. And then if we go ahead and copy this path at the top here and just tack that on to our directory here, we'll see that there's a CPU max section which we can read to see what the max CPU is that we can use in the system. We're going to switch out ls for catch here. There's our limits, and we could do the same thing for memory. By default, when these limits are breached, the Linux kernel will terminate the offending process. As stated in the Docker documentation about what a container is just an isolated process with all the files it needs to run. So we're looking and dealing with nothing more than a process here, and that's what a container really is. Thank you for your time. I hope that really gave you some deep insight as to what we're actually dealing with here, and that through your journey in your career, this information will help you when it comes to troubleshooting problems with containers. Now, if you've already reached this far and you found some value out of it, support the channel by giving us a like, subscribe to the channel, and show your love in the comments. And if you're looking for some more content that'll aid you in your learning journey, I got more Docker stuff right over here.